two directions. As you can see in the device, it has two alignments, the verticals and horizontals. So the vertical ones take care of the vertical stress, so which is the normal stress, the sigma here. So you have a normal loading applied to your soil specimens, and then if you divide by the area, then we got the vertical stress. And for the horizontal directions, we have the shear stress. As we can see from the apparatus, you connect to the shear load, the load cell in the horizontal directions. You can measure the shear load, and if you divide it by the area, then you get the shear stress. And we use the Greek letter tau to represent shear stress. And the whole thing will allow us to establish the Mark-Coulomb Ferrier envelope. You need more than one test, and this presentations will walk you through how to establish the parameters C and phi based on at least 4 direct shear test results. And this test has 3 steps or 3 phases for testing. So we start from the specimen preparations. So we constitute the dry sand samples for this lab, and then you will do the consolidations. Even though we test on sand today, and the for consolidating sand samples, you just take seconds, or just take within like minutes, then the consolidations will be finished. But remember, from 366, when we testing on clay, the consolidations can take a long time, and this phase highly depends on the soil type. And last but not least, the main majority of data that we collect will be on phases number 3, the shearing phase, where you can establish your stress strain curve for each test. So sample preparations again. So you will be proofreading the sand samples. We have done a demo, and then inside this like a shear box, and this shear box have the top part and also have the bottom part, and then like during the phase 1, we use the pin to make sure the 2 parts stay perfectly aligned with each other. We put down our triple disc and our brass disc, and then we do our sand proof variations, and after that we will put the top brass disc and the loading cap, and also the another triple disc when needed. And because it may not be perfectly happen that your sand samples will be perfectly aligned as the rim of the top box. So any like difference, any like the gap, either like below the rim here or above the rim over there, we can use a caliper to measure. So the thickness or the gap here, let's call the distance or displacements or measurements X for now. And how much sand when we prepare the samples we need, so we will calculate from the density. So the density will be mass over volumes, and from a target density, the volumes, so you can back calculate the mass that you need. So those are the procedure. Usually like we will give an estimate on how much mass that we should prepare, and it depends on the density range that you're looking at. And for this test, we are targeting constructing a loose soil samples. So we through the demos we talk about this. So in order to prepare loose sand samples, we want to have a zero drop height. So remember, like we proofread the sand samples through the funnel. So this is the funnel. The sand particles are filled in the funnel. and then we use dry perforations. We drop it inside the shear box, and during the progress that we perforate the sand, the distance between the tip of the funnels and the surface of your sand layers, this is the drop height. And we want to keep this drop height as minimal as possible, such that we can reconstitute the loose fabric or the loose configurations or loose structure of the sand specimens. So this is loose, and for dense, oftentimes we will need to apply vibrations in order to densify, or compactions to densify the sand particles during the preparations. And vibrations is more effective. Vibrations under normal loading is the most effective way to densify sand samples, just like the maximum density test we have introduced in this class during the first week. So that's how much sand we need. And next, we want to calculate the height of the soil samples, and you will be it can be calculated by knowing the total height. So let's call this is the total height of the two boxes. Let's call this like a H star. So H star is the thickness of the tube box minus the thickness of this 3 triple disc. So this is number 1, number 2, and number 3. So we have like a 3 other components inside the box that are not soils, and you 3 minus the thickness of those 3 discs, and minus or plus depends on whether the soil is below or above the box rim. In this case is below, so we will minus the gap that you have right there. Then that gives you the height of the samples. So you know the height of the samples, and you know the diameters, which means you can find out the area, and then times the thickness. Now we got the volumes, and you know the mass that you pull in, or you can keep track with the mass that you pull into the box. So you know the mass, you know the volumes, then you can calculate density. So after you calculate the density, you can check yourself whether you're loose specimens or dense specimens under those density range. So that's pretty much just the specimen preparations. Hopefully these presentations can complement with the lab demo that we videotape in the lab. So give you better ideas on how the tests are being conducted. And after we finished our specimen preparations, then we can start our second phase, consolidations. And that pretty much is the case where we apply the vertical loading. So go back to our video demos. Those are the phase that we put the dead weight on our hanger. So the hanger is the vertical alignment of your simple shear device, not simple shear, direct shear device. And the whole thing, the setup is the top cap, or the top box. The top box will be kind of like restricted on the horizontal movement, but it only allow to freely move in the vertical directions. So yeah, you can take the verticals loading. And for the data given to you, since this is an individual report, so we only have 4 vertical stresses that you need to work on: 15, 45, 60, and then 75 psi. So we prepare those dead weight representing those stress. So for example, if we have 15 psi of vertical loading you want to target for, which means 15 pounds per inch square, you multiply that by the area of the soil samples, then you will get the certain amount of weight that we need to prepare. So if we put all this weight to the one-to-one hanger, then that's how we prepare the vertical loading. And once we place this all this weight on the vertical hanger, then we finish our consolidation phase. And we want to keep track with the vertical deformations with the dial gauge we install. And on the videos, we also showed you the device that we have in our lab is capable to do a 1:10 ratios of loading because it has a loading frame. So if we this loading, especially when you come up with the largest one, 75 psi, this becomes huge. Maybe end up like a calculation tells you need to prepare 200 pounds of weight, and you don't have that much that weight in the lab, then you can take advantage of the lever system that we have on the loading frame. So instead of 200 pounds that you need to prepare, you can just prepare like a 20 pounds, and based on the loading frame, that you can like scale up the loading from 20 pounds to 200 pounds. So once we add on the weight on the consolidation frame, we record the vertical deformations, then we finish the second phase. Then after that, that will be our third phase of this test, which is the shearing phase. Very important before we shear or we start cranking our motor. We need to make sure we remove all the screws, the pins that keep the top and bottom box perfectly aligned, because now you want to mobilize the bottom box while the top box is kind of like restricted in the horizontal directions. So that's the whole idea. So this will be stable, but this one you will try to move this freely in the bottom part, and then the top part, this is connected to the low cell. So this is the low cell, which is in our lab uses a wing, and then with a dial gauge, and the dial gauge will tells you how much like deformations within this metal wing. So pretty much is like a low cell. So so the bottom part want to move, and you would drag the top box with it, because there's a string of frictions. So the soil strings happens here. The frictions or the soil string to try to drag the top box go with the bottom part, but the top box is being stabilized there. So whatever you measure from this low wing represent the soil strength, and the soil strength depends on the shear displacements. So if you plot this out, this is the shear displacements, and this is the shear strength. So if you plot at different displacements, you keep reading your dial gauge, and then you get different data points. So this is how you develop the stress strain curve based on the setup. Because actually, this is shear strength, or what you were recorded as the loading from the load cell. And if you have the load divided by the area, they give you the stress. And about the direct shear apparatus that we have in the lab, the recommended shear rate that apply is 0.006 per minute. So that's why when we manually mobilizing or cranking the motor in the lab, we want to do it as slow as possible to mimic the shear rate. And ASTM standard has its regulations or its recommendations for a particular shear rates to be used. And the loading frame has a ratios of 1:10. We talk about that in the consolidation phase. and also there's a low cell calibration factors. Okay, so the low cell calibration factors is 0.198 pounds per 0.001 millimeters, which means like from the low wing. So if this low wing got like a depth deformed, so this is the top view of the device. So every like a tiny bit of a deformations. So this is the total like length of the steel wing, and this is the small deformations. So every tiny bit of movement as small as 0.001 millimeters, representing the change of loading of about 0.2 pounds. So whenever you get deformed by 0.01 millimeters, the soils is experiencing 0.2 pounds. So that is the low cell calibration factors. And how far we want to move at the end of the day, we can cap the movement because of the time restraint that we have, because everything move very slow. If you want to finish the whole test, there's about like a 45 minutes over there to finish one test. And the total distance you want to move, you want to move less than 0.5 inch. So that's the limit of the shear apparatus. And also we stop the test at about 10% shear strength, and shear strength is defined by so let's say this shear displacements to be delta x divided by the height of the samples. So this is the shear strength. So this is the height of the samples. So we have that divided by h, and that's just the shear strength. So how much like you want to stop? So this is kind of like the limits of the device. You should stop at this number for the safety for the device. But before reaching this number, when you reach 10% shear strength, you should stop the test too. And how much is 10% shear strength? So we know this is 10%. We can calculate this. That will be equals to the delta x divided by the height of the specimens. So you know this one, then you can back calculate the delta x. That will be the travel distance that you want to have for your test. So a rough calculation is like the whole test will take about 40 minutes. So when we're doing this in the lab, we break down into groups, and different groups will take care of different like a stress level, because in order to establish the molecular failure envelope, you need at least 4 tests. So which means at least we need 4 groups right there to get the test done. And each group you need like a couple of students to work on it, because when we do the test manually, we need at least like 3 students reading different dial gauge, the vertical and the horizontal movement, which representing by a dial gauge, and also you need to read at the low cell, which is another dial gauge. So you have 3 gauge that you need to take care of, and also you need a cranker to move the shear box, to move the device by turning the device slowly, and also you need a timer. So a timer to call out at certain times everyone need to read the dial gauge. So at least 5 people to get one test done, and we have 4 groups, so we can at least get 4 data points. So on the Google Sheet, so this is the Google Sheet that we have, and I have already provided all the needed data for you to interpret the data and do the calculations. So there's 4 tests at different stress level at 15, 45, 60, and also 75 psi, so pound per inch square. And the specimen diameters, the specimen height, and also already provided you the density of the test. So you have all those informations, and also provide you when before we start making record of those dial gauge, what is the initial readings. So you will need those initial readings to for data interpretations. So, and those are the data that we record in the lab. So first, you need a timer. So at about every 5 seconds at the beginnings, and more like increments difference later to record the data. So we have a schedule here on to record the data. So at 5 seconds, at 10 seconds, and 15 seconds, and later maybe every 20 seconds, the timer will tell read, and there will be a different recorder recording the shear force from the device, the vertical displacements, and also the horizontal displacement for the device. And how to interpret those data? First, that need to go to your lab report. So in order to change now the shear force from kind of like a raw data you directly measure from the readout from the device, you need to convert that into an engineering unit. So to do that, we need to take advantage or make use of the calibration factors. So the first thing you would do is you would offset the dial gauge first, because when we start recording the data, the dial gauge is not necessary, or you don't want to that way too. You don't want it to start at 0, first. It's very hard to adjust the gauge or the pointer to be exact at 0 positions. So and then you want to have the spring, so pretty much the dial gauge is the spring, to work at your full capacity, which is at the midpoint of the spring is the most accurate position. So you want to have some initial readings to record the data, but after that, when you do the interpretations, you just need to correct for it. So now is we do the data corrections. So the very first step you do is you take the readings and then minus the initial values, and you want to anchor it. So that gives you an offset, so you go back to 0. Okay, so here again we correct for the offset for the shear force. So we have the readings from the dial gauge minus the very initial values. Make sure we anchor it, and then multiply the calibration factor. So this helps us to convert the millimeters to the engineering units that we want, which is pounds. And make sure we anchor it, and this is per 0.01 millimeters, so we multiply it by thousands. So with that, then we change all of the measurements from millimeters to pounds. So the next step is convert this to be to the stress. So if you have the loading, divide by the area. So I let you to calculate the area by yourself. So the area pretty much now you have the diameters, so you should be able to calculate the areas. So the loading divided by area, you get the stress, and then also we need to correct the offset for the vertical displacements and also the shear displacements. So very similar. So for examples, when we have the vertical displacements, we have this minus our very initial values, which is, well, like the readings at the 0 seconds, or the values after your vertical consolidations. So the difference between these two numbers here represent the total deformations that you have when you apply the dead weight. So I don't require you to do anything like on these two numbers, but at least I want you to understand where they come from. So the difference between the two are the deformations from consolidations, and the final vertical displacements pretty much is the very last point at the end of consolidations, which means at the beginning of the next phase, the beginning of the shearing phase. So this number here should be matching this one. So if you have all of your data subtract from the offset, then you correct and then you drag this down, then you have corrected for the vertical displacements. Very similar, you will do the same thing to correct for the horizontal displacements. So you can either like subtract everything from this number or this number. They should be the same, the initial vertical displacements. So after you do all this calculation, so I'll let you guys to do it. So you should do the calculations yourself. So after we finish all the calculations, then you have the shear stress. If you plot this with the shear displacements, then give you the stress displacement curve. So which is required later. So we talk about all the data collections and also the interpretations. Next, you need to plot your curves. You will have 4 curves for your lab report. So you will have the 15 psi, the 60 psi. You need to use different like colors and let me try to do this. So when you do this, you will use the different colors, you know, and to distinguish between each task. So in Excel, you will do this. So this is the 15 psi of the vertical stress, and then next you will do another one. Oops. Something like this for the different data point, and this will be your 30 psi, and you will have two more tests. And then you have use other color and use different like, you know, different marker. Then you will have like the 45 and I think this should be 45, right? So 15, 45, 60, and also 75 psi. So we have 4 tests, and you have 4 curves right there. So this will be another vertical stress. This will be another vertical stress. So you have 4 curve, 4 stress strain curve. So here I didn't ask you to calculate the strain. So pretty much this is the displacements. So the stress displacement curve. So I try to make his life a little bit easy. So this is the stress. No, this is the shear stress. So this should be the shear stress, not the normal stress. So this is the stress, and this is the displacements. The next step, you should convert the displacements into a strain. But now I don't require you to do that. Stress displacement will do the job for your education exercise. And next, you also need to calculate the expected well, the other graph you need to include in your lab report is vertical displacements. So this is your vertical displacements, and this will be your horizontal displacements. So if you go back to your spreadsheet, so this will be your vertical displacements, and this will be your horizontal displacements. So you plot like between those, like a four curve again. So you may not change much. You may like do a little bit like this. So one test, and then you use the other color. Then you may do the other one. So you have like a four tests there. So this could be the vertical stress equals to 45 psi, and this could be the one that the vertical stress equals to 75 psi. So 4 tests, 4 curve. And then next, then you should able to establish the Mockram failure envelope based on the results. Because if you go back to those stress strain curve, so for examples, for the 15 psi, you know the vertical stress is 15 psi on the x-axis. So this is your x-axis. So you have the 15 psi. And what is the corresponding maximum shear stress you will get from there? So for example, this is the 15 psi, and this is the maximum point. So if you go back to the y-axis, then you get the tau max after 15 psi. So you get your first data points. So it could be here. So this will be your tau max 15 psi. So you also do it for 45 psi, 60 psi, and 75 psi. And for each test, you have the stress strain curve and also the corresponding maximum shear stress. So you will have and about that one here, that one here, and that one there. So with 4 data points, then now you can feed in like a straight line. So I try to draw a straight line there. So this could be the straight line that you have feeding the 4 data points, and the slope here will be the tangent free angle, and the intersect here will be the cohesions. Because remember the Mockram failure envelope, which is the shear stress, which is the y-axis here, is equals to the intercept. So here plus the vertical stress, which is your x value now. So this is effective stress base, and then times the tangent phi pi. So pretty much like this is the slope, and this is the y-intercept. So with that, so that's why we need like a 4 data points in order for us to find the phi angles and also the cohesions, the y-intercept. So those two phi pi and c pi are very important for design, and those are the soil properties that we want to find out from the lab. So we test on the sand samples, and we spend all this effort to establish this graph. Then we can define the friction angles and the intercept for the sand that we test on. So what sort of error that may come from this lab, this like a test? First, like remember, the whole thing, you come with like a 2 box, the top and bottom part. The top box and the bottom box make up the shear box, and we force the failure. So the direct shear box is something like this. So we are forcing the failure happen as the shear plane here. So that's what we call the P-defined failure plane, which is not a good thing, because if you have features in the soils, it is not failing as it wish. So it's not a it's not like the weakest plane that caused the failure, but we forced it happen at the middle. So it's not a good thing that becomes like one of the source of errors. and also inconsistency like specimen density. So we rely on this 4 tests that has our similar density, such that like we're comparing apple to apples. So if you have one test that being like much denser than like the other 3 tests, then sometimes you want to redo the test. Otherwise, like you are not having a friction angles and a C point that representing the density you're looking at. So this lab, make sure like one of the difficulties will be reading those dial gauge. Make sure you learn how to read the dial gauge, and also the improper data interpretations also give you the one of the source of the errors. So I also provide some lab questions for you to think of, and since like you have individual reports, so I don't require you to work on the lab questions. But for those who want to have a deeper understanding in this topic, I highly encourage you to think about those lab questions. And if you need help or you want to discuss with me, please come to my office hour. Then I can I'll discuss all this like a fun technical contents with you.